بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم. حسبنا الله و نعم الوکیل، نعم المولى و نعم النصير. Last time we were concluding the inverse kinematic problem of serial manipulator with the method of successive screw. Today I will review this method and forward with two 6 degree of freedom examples that show how effective this method can be used. Our golden rule in screw method is that any vector in reference frame can go to the target frame toward the successive number of screws which are represented by the homogeneous transformation that we call it AI for each screw $I. And two techniques are used here. They are not very algorithmic. They need some intuition to do that. But the technique that we are using is, first of all, we can use a number of homogeneous transformation inverse, or the transposition of the rotation matrix actually. In the other side, this P0 is usually very simple. This P1 is the general form of the end effector position and orientation, which is given to in the inverse kinematic problem. And the AIs are depending on the joint variables. So there are some unknown variables in each of them. The joint variables could be either theta i's or d i's, depending on the revolute or prismatic joint that we have. So the first technique is find a good appropriate point P, which is usually the wrist of the manipulator, not the end effector, to reduce the number of the screw axes that we need for this transformation. If this is only 3, it would be very, very simple. If it is more than 3, then it is a bit harder. And then having this equation in mind, find the inverse of one of them, bring it to the left-hand side to separate the equation in a way that can be solved further by the manipulation we gave it in previous section. So the manipulation that we can use is no difference. You're using the screw or you're using the Denavit-Hartenberg problem. You can use ATAN2, you can use a linear equation with a matrix equation for a parameter that can be solved. You can use half tangent, you can use geometric approach. Any means that you can solve this nonlinear equation should be considered in here. This is usually used for the positioning vector and finding the 3 or 4 first joint angles or joint variables. And then for the orientation, we use other vectors, not position vectors, orientation vectors. The orientation matrix of the end effector can be represented by a rotation matrix. This rotation matrix can be represented by 3 UVW versions. Again, this UVW in the screw method, you see that we can find them in the reference position when the robot is fully extended. Very simple. You can find the UVW with a reference frame quite easily, and these UVW are the orientation of the target point that is dependent on the orientation of the end effector and are dependent on the task space variable which are given in the inverse kinematic. Again, which one to use, it is quite dependent on the problem, but you find the one which gives you the simplest variation in here. In this orientation, as you see, we have all 6 R's here. We don't need the homogeneous transformation for orientation. We can use only the rotation matrices here. And since in the first part we have find the first 3 or 4 parameters, we can use these 3 or 4 unknown rotation matrix, bring it into the left-hand side. This is totally given now, and this part is not given. And then you write the equation here and try to solve them by rigorous mathematical inspection. Of course, this should be verified through examples, and the 2 examples I'm giving here are very difficult. If you don't know this method, it is quite significant and challenging to find the inverse kinematic. Do you understand the total concept of this idea? Let's go through the examples. The first example is a 6 degree of freedom elbow manipulator, which does not satisfy the Pieper relation. The Pieper theorem says that if 3 intersecting joints are available, we can find the parameters quite easily and the inverse kinematic quite easily. In this manipulator, which as you see it has a rotation out of the plane, and then we have a similar 2-arm manipulator, and the elbow up and elbow down as we define for the parameters. And finally, the wrist doesn't intersect at a point. As you see, there is a A4 here. The wrist is not quite simple as in the Pieper theorem. We have only 2 intersecting. This point P has 2 intersecting, has 2 orientation on top of each other. But the real wrist, which is at this point, has actually 1 length A, so we don't have the 3 intersecting parameter here. It is quite difficult for such general cases. Of course, it is easy because all the parameters are rotational, all the joints are revolute, and we have 6R manipulator. It is not the most general 6R manipulator, since we have 2 intersecting variables or axes at the wrist, but it is quite extensive problem. We have solved the same problem back to the forward kinematic analysis, and we find the screw transformation quite easily. As you see, we have 6 theta, theta 1, theta 2, theta 3, 4, 5, and 6. And this link length can be found by the forward kinematic approach. So these are given. The parameters within this matrices are unknown, and we would like to find them. So keeping this in mind and considering that we don't have an intersecting point here, the first example, the first problem that is to solve the positioning here, we can say that in this manipulator, the position and orientation are not just decoupled. We cannot do the decoupling approach that is given in the Pieper solution, but still we can use this equation to find the general inverse kinematic problem. Let's see how we can do that. We use the point P here, not this point, the point P, which has the 4 consecutive screws. First one, second, this is the first one, the second one, the third one, and the fourth one. We have 4 screws, so A1 to A4, we can reach to the point P at this point. So we use this equation quite effectively here, we say that the position of that risk point, P, in a general configuration, which are given by Px, Py, Pz, we can find them from the end effector manipulator position. If this is given, this can be found by the golden rule of the screw, successive screw mapping A1 to A4, the same position at the reference frame when we have the robot fully extended, and then we can find this relation like that. And the fully extended P1, P0, as you see, if we have fully extended variable, we have A1, A3, A2, A3, and A4 just in the X1 frame. So you can find this very, very easily. The P0 is A1, A2, A3, A3, A4. The addition of this length at X0. And when we have the orientation, when we have the mapping here, this goes to Px, Py, and Pz. And to make this equation easier, we use a 1 minus 1 as we discuss it here. Usually we bring it the other side. We put this one here to make it easy. Now, A1 is a function of theta 1, so A1 inverse can be easily found by symbolic manipulation or by hand. The rotation matrix is the transposition, and the position matrix is 0. Here it is very easy to find A1 minus 1. So we multiply this to Px, Py, Pz, the left-hand side, keep it in mind. And then we have this part, which is a bit difficult to manipulate. A2, A3, A4, again, we use the symbolic manipulation. We multiply these three component that we have in here, A2, A3, and A4. And you see that the rotation matrix is very simple. The addition of triangles, because they are in a plane, so the addition of them is about y-axis. And what the positioning is a bit long, as you see in here. Again, in the positioning also, we don't have any y-axis because all of these three vectors are in a plane, and only the A1 was out of the plane. And we take the A1 on the other side. So we have this should be multiplied. This should be multiplied by this vector, A1, A2, 3, 4, 0, 0, 1. This make it much easier. So we go only with this one, and the last part is equal to the left-hand side. And let's see what is the left-hand side. If we multiply this to Px, Py, Pz, we find this part. This is the left-hand side of the equation. And this would be the right-hand side. As I mentioned, the right-hand side is quite easy. And when we multiply this vector to this part, we have only the last equation and the first equation. And as you see in here, we have the last equation and the first equation here. So this manipulation will result into this part. Up to here, the method is different from the Denavit-Hartenberg to screw. The screw is easier in a sense that you don't need you have the target position and reference position point. But from here to solve the problem is the same, as difficult as what we have in the Denavit-Hartenberg method that we used before. You should look into this equation. Of course, this equation, one of them is very simple. You find this one very simple, and you can find theta 1, since this is 0, very, very quickly from this part. You see that the sine and cosine is given, so the tangent inverse of px over py over px will give you the tangent of theta 1. And here we have two solutions. Since we are not using a tan 2, we're just using one simple equation, we reach to two solutions here. And these two solutions means that the positioning could be, with 180 degree difference in terms of the theta 1. And now when theta 1 is given from this equation, then we should go to theta 2, theta 2, 3, theta 2, 3, 4. So we have three other equations, three other unknowns, which are not very simple to find by these two equations. Keep these two in mind. We have theta 1, we have the left-hand side quite accurately known, but these two equations are not sufficient to find three other parameters. We go to another screw representation, and here we use the W1. The W1, why W? We use UVW, and the one which gives us, like here, gives us at least one simple relation would be very useful to be used in here. So as you see in here, we go through W, and W, what is W0? If you go to this part, and if we have the fully extended one, as you see the W, which is in this direction, in Z direction, would be in X0 direction, and in Y0 direction, W, it is at this point. When we have W0, we can find that W0 quite easily, but the W is a general orientation of the manipulator, which has WX, WY, WZ, the three given component, and we use now the W1, as you see here, we need all the screw coordinate 1 to 5 coordinate, not the sixth one. The sixth one is around the W. So we use the W to just remove the sixth one and use the all 5 rotation matrices. And as before, one of them we bring it on the other side, and hopefully this one is already given. So R1 is known. This is the whole left-hand side is known, and the right-hand side is depending on 4 thetas, theta 2, theta 3, theta 4, theta 5, but since W is very simple, 0, 1, 0, if you multiply this all together and to W, you reach to this 3 equation, which you see this is also simple. Not very simple, but it is simple. Now we have 2 equations here with 3 unknowns. We have here 3 equations again with 4 unknown. Now we have 1, 2, 3, 4, 5 equations with 4 unknown. The number of equations is sufficient, but it is not clear that we can find the solution quite easy or not. But as you see again, here we have one example here which is very, very simple, and that's why we are using W0. If we use U or V, the equation would be not that simple. We have the S theta here, and we have also the C theta, theta 5 here. We have the cosine of theta 5 here multiplied by sine, and this gives us a very good solution to use basically 2 solution in here. We use the inverse sine by this equation. We find theta 5, and then when we have the theta 5 here, then we have the cosine of theta 5 here. We have the sine and cosine of theta 2, 3, 4, the addition of these 3 angles in here, and we can use atan 2 to find the inverse. From 150, we solve it for the inverse sine. Again, here we have 2 solutions. We had already 2 solutions before. Adding these 2 together, we have 4 solutions for the inverse kinematic. And theta 2, 4, 5, we use atan 2, since we have the sine and cosine 2 equations here. We use the atan 2 to have a unique solution for the addition of that. Still, we don't have the separate theta 2, theta 3, theta 4, but the addition of them is defined quite well. Now that these two equations are found, we will go to find for theta 2 and theta 3 if the component of these two equations. There you can go back. If we go to the first two equations that we have, since we have the theta 2, 3, 4 given, these two equations, this part is given. Now we have two unknown, theta 2 and theta 2, 3. We bring the known variable to the left-hand side. We have two linear equation with two unknown, theta 2 and theta 2, 3, theta 2 and theta 2, 3. We can find both of them by a linear manipulation. As you see here, I write the equation, with some parameter. The known variable, I put it on the right-hand side, which are quite easy. The previous one plus this part that is bring it here. So we have two equation, two unknown. You use an inverse matrix. You have a matrix A2, A3, A2, A3 for this sine and cosine here. You can find quite easily by the matrix manipulation, or simply by summing the square root of that. We have sine of theta here, cosine here. We can just add the summation here, summing the square of these two. These two will go out, these two will eliminate, and only theta 3 will remain in this equation. And then you can find the cosine of theta 3 as the inverse cosine here. Again, here you have two solutions since we are using the cosine variable. When we have the theta 3 given, then the theta 2 will be quite easily find from this equation, and we can finalize when we have theta 2, then the theta 4 is found just sequentially as we go forward. Therefore, the only parameter remaining in the inverse kinematic is theta 6, which we didn't touch it yet. Since we have used only R2 to R5 here, we didn't have the theta 6 in here. Now we use another screw relation. Again, no one can say which one. You should try them. We use U0 here, and the U0 goes 1, 2, 3, 4, 5, 6. All these 6 are given. Let's go through this. When we say U0 is this direction and this direction, the orientation of the end effector will also change that. So we can use either U or W. Here we use U. U is give us the simpler relation. And since we have the theta 1 to theta 4 all given, instead of bringing the variables, we can put everything in here. Hopefully, this manipulation result into this 3 equation as you see in here. And we have in here only one parameter, unknown parameter, which is sine of theta 6. The theta 6 with the sine is given here and the cosine is given here. Now we can use either of these 3 equations to find theta 6. One may simply use this equation and inverse cosine here, but we rather use autan 2 to don't have duplicated solution. We go here and use these 2 equations. As you see, we have sine of theta 6 here, sine of theta 6 here. It is quite simple to just eliminate this. It is simple to multiply this equation by sine of theta 5, this one was cosine of theta phi, and then just take the, not the addition, the subtraction of these two, sine of theta 5 square plus cosine of theta 5 square will eliminate it, and the sine of theta 6 will be apparently seen in here. As you see here, we have the sine of theta 6, we have the cosine of theta 6. We can use tan 2 to find a unique solution for theta 6. And by this means, you will see that all the 5 theta variables are found, but quite heavily and challenging. Any question, anything to be, any comment or question, please?
Excuse me. Is P always at the wrist?
I don't have your voice again very clearly. Is the P point always the wrist?
Yes.
Your question is that? Yes. Yes. Usually, we cannot say always the wrist, but what we are doing, keep it in mind. We would like to decouple the position and the orientation. So we use a point where the orientation of the end effector could be decoupled from the position. We cannot say that here this is the wrist or this is the wrist. If you call it maybe mechanically this point is the wrist, but since the PFR solution does not exist, we have 2 points at the wrist. We use this point, you can call it wrist, to just decouple the orientation, the 2 parameters, theta 5 and theta 6, orientation of that from the positioning of the system. So this is very, very commonly used. Of course, you could use you could use either this point as well. But this point really does not give you the orientation. Then the orientation would be much difficult to find. We try to find either the third or the fourth point or the joint at the intermediate point that we can decouple the orientation and the position.
Okay. Also, I didn't get completely what's the difference of the screw methods with PFR's method other than it's more generalized.
It is this one. If you have examined and tried to find the successive screw method for forward kinematics, you could find what is the difference. Here you see, this equation, do you agree with me? This is the general golden rule for the screw. Yes. If you go through the example here, you see here, P0 is found very easily. Much, much, much easily than the Navier-Hartenberg problem. Okay. This is the difference. The only difference is this. Other than that, you have the same inverse, the manipulations are the same, but writing the formulation is different. Of course, AIs are also different. These AIs are not the TIs that we use in the Navier-Hartenberg. This is the screw-based one. It might be a bit more, not difficult, it is different. Of course, we can do that all with symbolic manipulator. We don't do it by hand usually. We use the computer to do that. But the main important difference is that this point can be found very easily. You see, not only this, we go to this, again W0 is very easily. Why we have only 3 equations here? This 3 equation, if you look at the W0 here, W0 is along Z. And along Z is along X1, and along X1 is along Y0. So we need only the second row of this equation. We have, if you look at here, we have a 3 by 3 matrix multiplied to each other, time a vector. But this vector is very simple. As this is very simple, non-zero, 0, 0, this vector is also very zero. 0, non-zero, 0, 0, 1, 0, we can say. And this equation becomes so simple. It is much simpler to find this. Of course, this manipulation is hard, but the solution, since you are multiplying this by a vector, it is much easier. And this is the main difference. In Denovitt-Hartenberg, you don't have a vector solution here. There are the matrix manipulation. You have to equalize two matrices to each other. But here we have two vectors. And these two vectors make the life much easier. Believe me.
Yeah, I got it. Thank you so much.
Any other question?
Excuse me, Doctor.
Of course, Hussein has also some question. The first one is Zahra, and the second one is Hussein. Go ahead.
In a real case, we must have a proposed or desired position and effector position.
Yes.
As here, and we started with we didn't start with the end effector position in our solution, in screw solution. It's more easier than DH parameters screw, yes. But we didn't start with the end effector. This is first parameter, Px, Py, Pz. And the other question, what about?
Let me answer that first, one by one. You're commenting, you're not questioning. And it is good. But let me answer that first. A very good point. The other people didn't maybe notice. But as you see, we are giving here Px, Py, P0. In inverse kinematic problem, P is not given, Q is given. P is not given, Q is given. But Hussein, look at that. What is the difference between P and Q? Very simple. We have only a D in Z direction. So if you have the Q, which is given to you, you can very easily find the P. The same way we did D in here, as you see in the previous example. You see here, when we have the Q, then we can find the P. So this is not a drawback. It is very simple. When we have the Q position, since we have only one part, one piece, which is the length of the end effector. The orientation is there. We have only the length of the equation. Here, when we go in here, when we have Q, I didn't mention how we find the Px, Py, P0. Of course, if you go to the book, it is given there, but it is not necessary to do that. So because it is so simple, if you have the P, if you have the Q, the P has only a difference D6 in the Z5 direction. Only this difference. So you can find from Q, you can find P. Now go to your second question.
Okay, thank you. Yeah, only perform an inverse translation and start this algorithm. You mean? Yeah,
exactly.
What about omega and UVW? Desired UVW.
Okay, what is the desired UVW? Very good question again. You know, inverse kinematic, what is the problem of inverse kinematic? Let me go back to the first you're having my here. This is my first slide in inverse kinematic. Do you believe me? You have my slides here? Of course. You know, in inverse kinematic, we say that given X, find Q. This is the problem. In forward kinematic, given Q, find X. Given X, what does it mean? Given X means that we have the position of the end effector as we discussed it before. We have Qx, Qy, Qz, and we have the orientation of it. It is given to us. This is the problem. Or the desired orientation, as you mentioned, it is better in terms of control. Given what orientation we would like to have. An orientation is given by what? Could be by Euler angles, could be by screw, it could be by anything. but we can represent it as a rotation matrix. So one part of this given X, one part of it is the position. Now go to our problem. One part of the given parameters is Qx, Qy, Qz. From Qx, Qy, Qz, we find Px, Py, Pz. One part of the given problem is the orientation of this end effector. The orientation is given by a rotation matrix. The rotation matrix can be written as UVW. That's it. UVW with respect to what? With respect to the reference frame. The orientation of the end effector with respect to the reference frame. So UVW is given to us. UVW is given to us. This is the problem statement, as we mentioned here.
Thank you. I also have a question, but for another time.
Go ahead.
We have infinite number of infinite configuration for UVW or what?
No, UVW, not infinite number. You can have any arbitrary. We can say you can have any arbitrary orientation. What orientation do you like? Do you want to be in X direction, in Y direction? You understand?
Yes, thank you.
It is arbitrary, not infinite. It is different.
Many.
Yeah.
Yes,
very good.
Thank you.
Just please close your microphone when you are not using it to have a better, no echo and better voice. This is our the very last example that we work out in here, and then I just give maybe very few important point at the end, just some remarks to conclude this session. And this year and this part of and this chapter actually. The second problem is again a 6th degree of freedom manipulator. Again, a very challenging example in inverse kinematic. And it is a Stanford arm. The Stanford arm difference from the other one is that we have a prismatic joint. It is not totally 6R manipulator. It is a 2R P3R manipulator. And it has the Pieper problem, the Pieper theorem requirement. The rest, which we call at P, we have 3 intersecting points here, S4, S5, and S6, as we have it in the screw coordinate. So we have 3 intersecting wrists, plus 3 positioning joints and links, but one of the positioning joints are prismatic. It is not revolute. And it doesn't really make the life much harder. It makes it different and maybe a bit simpler, since when we have a 6R manipulator, the theta manipulator, the theta problem comes with the sine and cosine into the picture. But if we have a prismatic joint, the D parameter come not with the sine and cosine, it directly comes into the picture. So usually the equations are simpler than a general 6R problem. In any case, what we do the same old. First, we do the forward kinematic. We have to find the screws. We have done that before, in a few last session, and we find the A1 to A1 to A6. And A31, as you see, is very simple. This is A1, this is A2, and this is A3. Again, we use the risk point for the positioning. Here we can decouple the problem. It is very easy since we have the Pieper issue in here, the Pieper case in here. We use the positioning of P in here, and again we use very simple P0 and P variables here. As I mentioned, the P is not directly given. Usually in a inverse kinematic, Q is given, this point. But the Q and P has only a H difference in the Z direction. So from one, we can get the other one quite easily by just a simple manipulation. So we go with the P. So we assume that Px, Py, Pz is found from Qx, Qy, Qz, and this H parameter, this H length of the end effector. And we use this relation with here. And hopefully, very simply, this is by only 3 parameters, A1, A2, and A3, which A3 is also very simple. So we have 3 unknowns here, theta 1, theta 2, theta 3, and you can find this equation going well. Of course, if you do the manipulation, we have a G difference here. In this manipulator, we have also an offset here. This offset come into the picture since we have the positioning here, the reference positioning here. This G also comes into the picture. The P position actually have a D3, and as you see, a sinus 1 and also a G1. This G1 comes into this picture. So simply by finding P0 and the general P, we have 3 equations with 3 unknowns. The 3 unknowns are theta 1, theta 2, and D3. Can we solve that? It is very easy, you know. It is comparing to this, very extensive problem. This problem is quite easy. You can find this 3 parameter one by one. How to do that? Look at this. First of all, we can use a physical inception that this P point, the radius or the difference from the P point to this A point really doesn't matter to the theta angle, and also doesn't matter to the other the theta 1 and theta 2. This means that if we just square this equation and sum them up, px plus py plus pz, we have cosine here, the square, sine and cosine here, and also here, and then simplify that. We will see that by summing it, the relation is only depending on the D3. The theta 1 and theta 2 will be removed, and we can find the D3 by a position plus and minus this equation. Of course, the D is usually positive. We don't have negative length for a prismatic joint, although there is 2 solutions. One of them is the positive one, is the real solution for that. So this is very general. We did it several times, as we see. Just to sum the square of this equation will reduce the complexity, and you can see from the physical interpretation that if the length of this point to here really doesn't change by theta 1, by theta 2, this doesn't change this length, only the length is changing by D3. This means that we can simply eliminate the theta 1, theta 2 from this equation, and this elimination is done by summing the squared and using the trigonometric relation in here. Now, since we have the D3, now the D3 is given. You look at here, D3 is given in theta 2. You can simplify the theta 2 here by sine, inverse sine, and this gives us a simple solution, but 2 solution, multiple solution. I would like to talk about multiple solution a bit more at the end. Multiple solution is exciting. I will talk about it later. Okay, as you see in here, so we have D3, theta 2, and then we have 2 solutions for theta 2, and then we should go for theta 1. And theta 1 is if we have the theta 2, if we have the d3, we have cosine of theta, sine of theta, cosine of theta, cosine of theta, two equation, two unknown. For cosine and sine, you can just simply solve for these two equations. This is a linear equation. You find the inverse of the matrix and find sine and cosine separately, and then use the tan 2 to find the final solution. And that's done. From the positioning point, we have three parameters find, the theta 1, theta 2, and d3, and we have basically had four solutions, but only two of them are valid here. The theta 2 is elbow up or elbow down. Both of them can be usually used in here. And now we should go through the three other parameters. The three other parameters are the orientation of the wrist, which is totally separate from here. Now that we have the positioning, we go through the W, U's, and V's, which one which is easier here. If we start with W, W0, again, look here, Zahra, Hussein, look, the interesting point is the W can be found very easily. Go to this picture. If it is extended, W0. W0 is along which direction? It is along Y direction. Do you agree with me? Very simple. W is along Y direction. So it's 0, 1, 0. Very simple. But what about U? U0 is along X direction. It's 1, 0, 0. U0 and W0. We can use both of them. As you see in these two, we use the U and W1. First, we find W1. The first three part was known since we have solved it at this light. We have all the three parameters found in this here. And these three parameters are unknown. We multiply these three together, which are three rotation matrices like Euler angle equation. We have this one, and you look at this, you see that in this direction, this one is the most simplest one. Do you agree with me? That's why we are using W. W was along which direction? Was along Y direction. So if you multiply W0 to this to W0, you find only these three equation coming out. This three equation comes out. What about this part? This is the comment of Hussein. We have the W1 as a general rotation. It is given to us. We multiply by these three equations that we have already found out. So we call it W3, W superscript 3, some new W's, which are all known. The WXYZ is given as an inverse problem, inverse kinematic problem, and the sine of theta to theta 2, the theta 1 is also given. These three are given, and this is given. So these three equations, we have three equations with two unknowns here. And we can simply, again, solve for theta 5, at least here. We can find it here by this equation. This is the simplest point, the pivot point. So we can find the cosine of theta. And also when we have the cosine of theta, then we have sine. We can use R tan 2 to find the theta 4. We have theta 5, and then we use the theta R tan 2 for theta 4. And the only things which is remaining is theta 6. And to do the theta 6, we have either this one or this one. We can use U or W. And as you see, U is in direction of X. So if we use U0, these three equations are used. We call this one, again, we use U1. This matrix multiplied by U, which is 1, 0, 0, will give us this three equation. This three equation is known here. And this part, again, like the previous one, we find it from the given parameters of the inverse kinematic problem. We find this. Now we have 3 equations with 1 unknown, and we can simply use these 2 equations. We can use either this one and just simply use the cosine of cystatic, but we don't go with that. Since we have more number of equations, we can use tan 2 here. Here we have multiplied this one by sine of theta 4, then cosine of theta 4, then we add them up, and then we have the sine of theta 6 in here, very easily sine of theta 6 in here, and furthermore, we have sine of theta 6, we have cosine of theta 6, and we can use inverse kinematic tan 2 problem to find theta 6 in here. And then the solution is completed, and you can look into my picture and biography to have some relaxation after this much of mathematics that we have given. Any other question? Anything not know to be more described in here? I just encourage you. You know, these are like what we call in Farsi, معما چو حل گشت آسان شود. We say that when the problem is solved, it is then much easier to, it seems to be very easy. When you look at the solved solution, it is much easier, but you should do it by yourself to see the details of this. And we have given to you in your first assignment, and the first part of your project, which is basically a surgical robot, Da Vinci, the first part of a Da Vinci robot, or some eye surgery robot. You have to use similar approaches to find the inverse kinematic problem. Any questions? I have only a few words to say, which are very interesting at the end. No questions? You are becoming so excited to hear what is the interesting point. The interesting point I would like to mention goes back to the first, again, to this first slides that we have in here. This was the first slide, existence of the solution, and this elbow up and elbow down. Now you can understand me. As I mentioned, we have multiple solutions. You see that we have inverse sine, inverse cosine many times, and this gives us plus minus theta. If there is a theta, let's say, angle as a solution, theta minus pi is also another solution, which we call elbow up and elbow down. The point I would like to emphasize in here is, the continuum of the solution, the continuity of the solution, and to look specifically at the point that we have maybe some limiting point. Let's talk it in simpler version. You think, when we are solving inverse kinematic problem, we are not solving it only just for one point. We don't say that if we would like to reach to here, what would be my inverse kinematic problem? Usually we have a path. We would like to move the robot from one point to the other one. And we know that this path, let me come into the picture, this path is usually continuous. We don't want to, jump from here to there. the robot should move. For example, consider that we would like to use a eye surgery robot, and we would like to move the peeling of the membrane of the retina, or doing some injection into the eye, or doing any very precise positioning and of the robot, or a simple painting or pick and place point. We would like to go from one point to the other one. So the positioning that we would like to give is usually a continuous function that we would like to move. And that means that we should solve the inverse kinematic problem, not just at the one point, but at consecutive point. Which point is very interesting. So if we have this point, suppose that we have this point, we have, let's say, 8 solutions for that. We find one of the solution which is appropriate to that. Then we go to the next point, which is a bit different from this. We have, again, 8 other solutions. Which solution we choose? We choose the solution which is very close to the previous one. Suppose that at this point, let me bring my arm in here. The picture is not that well. We have 2 solutions. Let's say elbow up and elbow down. We are moving here. If we are moving here, the solution should be continuous. The theta should be continuous. So if you are elbow up, we are always elbow up. If we are elbow down, we go always elbow down. So if we have 2 solutions, we choose one of them as the first point. We use that, the same style of the robot as the other one. Only one point is very critical and singular. Which point is singular? When these 2 solutions, become one double solution. Look at this one double solution. Suppose that we go to the end of our workspace. If we are at the end of our workspace, I'm fully folded arm. A point before that, I'm not fully folded. I'm fully folded, and then I cannot go further in. I should come back. My trajectory cannot go further cannot go out of the workspace. It should come inside. But when I go at the end of the workspace, now I have 2 solutions which are very close to each other. I can go elbow up again or elbow down. Because the position here, the theta is 0, the first position could be plus or minus a small number for the theta. This point is quite elegant. And we call it singular point. And there is many issues related to that. We cannot just talk about the positioning of this point to find the whole concept here. We should talk about some velocities, the differential kinematic here, to understand the physical concept in here, which is very important. This is the issue that we will talk in our next session after the holidays, hopefully in 3 weeks. But what we see here, as I mentioned, look at this double solution. Double solution is very good. It has 2 main important. One main important is the double solution. When we have a double solution, we are at the boundary of the workspace. We can find the workspace. And I gave you a research to find interval analysis, how the interval analysis can be used to find the workspace of the system. But secondly, which is more important than just the workspace, this point is a different point than the other point in the workspace. Not only because it is at the origin, at the boundary, it has some other issues which is dependent on the velocity or the direction that we can go. Let's talk about the direction. When we are at the end, at the boundary of the, let's say, I should go a bit back to see my hand. Suppose that I am fully armed, fully extended. I am at the double position. At this double position, I cannot go further out of the workspace. So this direction is forbidden, but the other direction is completely possible to move. You know, I can go with this direction on the radius that we can talk. So it means that some direction of the motion becomes not possible to move. This means that we cannot have velocity in that direction. And this is very interesting. Inverse kinematic is related to some differential kinematic that we call it Jacobian. I don't give further notice here, but remember that we will come back to this point with more physical insight, which are really interesting. I can assure you that if you find the physical concept of that, you will be more excited than me as I am with you in concept. Just give you some very physical examples, some questions that is also very, at this time of the year, usually Iranian people will clean up the home and do some issues like that. Of course, I suggest you also to clean up your bad feelings and bad behaviors, just remove them from your soul. This is the part that you can use at Nowruz, which is the New Year of Iranian people. But at this time of the year, usually one of the things which will be done by usually the children at the home, they should help their mothers and their fathers to clean the curtains. I don't know if you have this experience. Of course, many of you have that. You should take off the curtains and then put them back. When you are taking off the curtains, usually the curtains are not wet. They are not very heavy. You can usually do that. But when you are putting back the curtains, this experience comes. Usually you have a lot of ache. It is not easy to put it back. It is hard to do that. Why this is hard? If the curtain is not up there, look at the curtains. The curtains are very close to the boundary of the motion. It's very similar to the point that we are ponder here. It's close to the boundary here. And it is difficult for us to do that. If you put the curtain, bring it down here at your workspace, you can very easily put it that without putting any pressure on your hands, on your muscles. But when you put the curtains up on the wall, on the ceiling, it is much hard to do that. Can we formulate this problem as a mathematical problem? Can we somehow relate this to some eigenvalue problem in a matrix? Yes, we can do. And very, very other important solution, I will give you some of them in the next session. Thank you very much for being with me. I try to make these two sessions a bit shorter since the mathematical problem is really heavy, and I encourage you to please consider do it by hand, by yourself. Follow the way that we are doing as a practice, and do the assignment and the project part 1 for the course. Thank you very much, and if there is any question, I am with you. If there is no questions, I wish you very, very happy new year and wish you health and prosperity in the next year. Bye. خدا حافظ. سال نو مبارک برای همه.
برای شما هم مبارک. خدا نگهدار.